Good morning all. We are discussing about magnetostatics. We have seen magnetic forces. Now let us see what is meant by currents. What you mean by current in a wire? What you understand by the current in a wire? The current in a wire is nothing but the charge per unit time passing a given point. Current in a wire is nothing but the charge per unit time passing a given point. We can write the current I as dq by dt. I is equal to dq by dt. It is the charge per unit time passing a given point. Now, what is the unit of current? What is the unit of current? Current is measured in coulomb per second. Current is measured in coulomb per second or ampere or ampere. One ampere is nothing but 1 coulomb per second. 1 ampere equal to 1 coulomb per second. We have seen point charge, line charge, surface charge and volume charge in electrostatics. Now you consider a line charge. Suppose a line charge lambda is traveling a wire. You consider a line charge lambda is traveling a wire at speed v. Now what is the value of that current? When a line charge lambda moving with velocity v in a wire, what is the current? Now you consider a wire segment in which the line charge lambda moves as shown in figure. This is the line segment, the wire segment in which the line charge lambda moves with velocity v, and you consider a small element dl on the wire, a small element dl. If it moves with velocity v, then we can write the velocity as dl by dt, as we have seen in the previous case. Then what is the value of the current? I is equal to dq by dt. Now if you consider a line charge lambda, then we can write dq is equal to lambda dl. Then the current I is equal to dq by dt becomes lambda dl by dt. I is equal to lambda dl by dt. When a line charge lambda moves with velocity v, we can write velocity v as displacement by time, that is dl by dt. Now substituting the value of dl by dt in the expression for I, we will get I is equal to lambda into v, lambda into v. That is, if a line charge lambda moves with velocity v, then it will constitute a current I is given by lambda v. A line charge lambda moves with velocity v in a wire constitute a current I is equal to lambda into v. We have seen magnetic forces. Now you consider the special situation. Suppose your line charge lambda is moving with velocity v in a magnetic field. Certainly, there is some magnetic force on the wire segment. Now let us calculate what is the magnetic force on the wire segment when the line charge lambda moves with a velocity v in a magnetic field. Now you consider a small element dl on the current carrying wire. Then what is the magnetic force on that small element dl when it is placed in a magnetic field B? We can write df magnet, that is a magnetic force on an element dl. This is nothing but dq into v cross b, dq into v cross b. This dq into v cross b is the magnetic force on a small element dl on the current carrying wire. Now, if you consider the entire segment of the wire, then the magnetic force on the entire wire is given by integrating df mag. The magnetic force on a segment of current carrying wire is given by integral df mag. This is equal to integral dq v cross b. Integral dq v cross b. Magnetic force on a segment of current carrying wire f mag. This is equal to integral dq v cross b. We know the value of dq. dq is nothing but a lambda dl. dq is nothing but lambda dl. Now substitute the value of dq on f mag, then rearrange. We have f mag is equal to dq v cross b. dq is nothing but a lambda dl. Therefore, f mag becomes integral v cross b lambda dl. Since lambda is constant, you can associate lambda with velocity. So the integral become integral lambda v cross b dl. We have seen that lambda into v is nothing but I. When a line charge lambda moves with velocity v, it will constitute a current I is given by lambda v. Now substitute the value of I. Now substitute I as lambda v in the expression. Now you will get f mag is equal to integral I cross b dl.